So we'll just go through all the other elements. This is oxygen 16, oxygen 17, still better approximation, even though not as good. And here we see that even though it's a better approximation, just barely, you can also see that the green line and the yellow line have intersected. And this also is a good indicator that the slope of the yellow line is not equal to that of the other lines. So again, here we are working with oxygen. No, sorry, this is already sulfur. Here we have the sulfur. This is the most abundant one. And then we have sulfur 33, which is not as abundant. Sulfur 34, oh, went a little bit too fast. Sulfur 34, still a better estimation. And here we have sulfur 36, which the difference in estimation is almost the same. Negligible actually, but still, it's still a better estimation. So clearly you can see if you allow the elements to have their own offsets, which of course makes sense, then they have a far better estimation than if you would have a shared offset. But of course, coming up with this method to make sure that you get the most freedom out of your system, even though they need to have the same shapes, is, well, not trivial to find. And this allows complexity to stay down while also having a really good estimator. I hope that was all well and clear. So when you look at these results, you see that actually oftentimes the error is now around 1 in 1,000, sometimes even less. And that is really desirable. It also has the advantage that now every element doesn't have a bias. And of course, as the elements don't have biases, it also allows you to state that the average mass of the protein will also be the average mass that you compute here. Now, with that being said, I also introduced a hybrid method. This has certain motivations, which I'll explain. But the basic idea is that you exclude sulfur from your data. Sulfur is rather rare inside of proteins, doesn't appear often, and as you look at how the fit goes, sulfur is actually quite deviating from the other data points. The other data points can be fitted quite neatly with a straight line, but you cannot do that for sulfur. So the idea was to only fit for hydrogen, carbon, nitrogen, and oxygen, and to have a separate part for sulfur. So you do the same method as I proposed just right now, and you do that for only hydrogen, carbon, nitrogen, oxygen, and then for sulfur, you actually compute the whole distribution that you will get. This will be a trinomial distribution. Now you can see that sulfur 36 is actually excluded. The reason that I do that is because sulfur 36 is actually appearing very infrequently. To reduce the complexity of the memory requirement, I actually say that it's not relevant, so I remove that data point. Now, of course, this isn't ideal, but it is a good enough approximation. To, however, ensure that the whole distribution of the sulfur is still intact, what I did was scale the other sulfur atoms with the position of the delta direct peaks, such that the average mass is maintained and that the variance of the distribution is also maintained. And you can simply do this by first shifting your distribution and then scaling your distribution around the average mass. Now, this allows you to have a good image of what's actually happening with the mass probability density, with well of with the probability density function of the mass, especially since sulfur has the largest variance of all isotopes. Sulfur 34 actually has a probability of 4.2% and sulfur 32 probability of around 95%, which makes it very spread out relatively to all the other isotopes. It's actually it gives a good image of what's going on and also clearly indicates the discreteness, which isn't always very neatly maintained in other methods. When you have sensitive measurements, you might be able to see this discreteness, where for the others, you probably wouldn't. Now, here we have some results on how well that actually works. So first we of course have the isotopes, then the abundance, then we look at what the actual mass will be in daltons, and you see that it has a complexity of 8 to the power 8, where A represents the number of atoms. Now, if you do just the least squares, then you'll also have a complexity of A, but you'll see that the error, although not too big, is significant enough. When you do a weighted, you also see that the error is redistributed, and you'll see that the isotopes which are frequently appearing inside of your protein also have less error. But now if you compare this with the same slope weighted least squares, the SSWLS, you'll see actually that for most of the isotopes, the error is reduced by around a factor of 100, sometimes even 1,000. It should be noted, however, that because you have a same slope nonetheless and only a different offset, it will mostly fit for the most abundant isotope. So you have to really look at all elements separately, and then you see that it actually gives a really good estimation. For example, if you look at the hydrogen and deuterium, you'll see for the same slope weighted least squared that the error is around 1 in 1,000. No, sorry, 1 in a million for the hydrogen with one proton. For the deuterium, you already see that the error is 1,000 times larger. That's still not large compared to what you would have previously, and it's also unbiased, but still, it is an error. Now, you can also compare this to the sulfate hybrid weighted least squared. And there you see that for most elements, you get a slightly better fit. Of course, since sulfur isn't in the picture anymore, some atoms would have a different, a less good fit, but in general, it's improved. Now, it should be noted that, of course, for the weighted data, I used a certain protein. I actually generated a random sequence. So, of course, this data is not fixed for every protein, but it still does give a good overview of how this method is still better than taking a naive approach such as least squared or just weighted least squared. Now, as you are aware, when you have a nanomass sensor, not only the mass affects the response of the nanomass sensor, also the stiffness has an influence on how the response of the system is seen. Sorry, I probably said that wrong. The stiffness of the object has influence on the response of the system. So if you are neglecting the stiffness of the protein, it could well be that you have an error in the mass estimation. Now, this combined with the fact that the shape of the protein is unknown for the most part, uh, it introduces a degree of uncertainty in your measurement. I would like to simulate that to get an idea of what is actually happening on that level and how much this variance in different shapes can influence the response of the system. Um, as you see here, for example, you have three modes where they used golden balls, which are placed on a nanomass sensor of a different type, and they actually were able to deduce the mass and stiffness, but they were also able to deduce that the balls had to be squashed because the stiffness measurements would else not agree with the measurements that would be expected from a theoretical standpoint. Now, whether the stiffness would have a significant effect also, of course, depends on the size of your nanomass sensor. The sensitivity of your nanomass sensor, theoretically, would improve with a smaller size. Of course, you would have different noise sources which would form an inhibition, but in addition to that, of course, the size of the protein would become relatively larger to the nanomass sensor when you're scaling down the nanomass sensor. Normally, you can just use three modes and deduce the mass and position of the object with these three modes, assuming it's a point mass. However, if you want to take a sensitive measurement, this does have an influence on how well you can actually take this measurement, because the stiffness and shape of the protein have a different response than if it would only be a delta Dirac peak, a point mass on a singular position. I'm interested in how this can actually influence the results, and therefore I'm learning computational multiphysics and trying to apply this model to a lifelike setup of a nanomass sensor that we could use for proteomics. Now, when it comes to Peter, I would actually like to discuss together with Sherman which setup is most likely to be used for proteomics in the future, such that I can actually make an accurate model of that. I also need to still find some good estimations of the Young's modulus and Poisson ratio of proteins. I have been able to find good estimations of the density. And the main idea here is that I'll plug in these values. So what I'll do is I'll get data from a protein database. I'll take, for example, a certain protein. I can simply deduce the mass variance with the program that I've written. From there, I can change the density. So I'll have a certain fixed volume, which I can deduce from the protein data. I have a fixed mass, so I have a fixed density, of course. But now the shape isn't necessarily fixed because you don't really know what happens when the protein squishes on the surface, especially since orientation would probably also matter in the final result of how it's oriented. So unless we're using any technique like electron tunneling microscopy, from which we could deduce the shape, or maybe atomic force microscopy, although I'm afraid that would damage the setup,